Hi there, my name is Charles Fosfang Msipa. Welcome to another tutorial presentation. Our presentation today is on binomial expansion.
Let's talk binomial expansion. Obvious, I'm thinking everybody knows that the binomial is a term with a is an expression with two terms, like we've got a plus b as a binomial. Now, if we evaluate this to the power 0, we know that we're going to get 1. That is clear to everybody. Then if we take this to power 1, we're going to get ab. Now, if we focus only on the coefficients of this a and b, a plus b, we can actually say this is coefficient 1 and the coefficient 1. I'm just extracting coefficient of this thing. Is that clear to everybody? Okay? Then if I take this to the power 2 and say a plus b to the power 2, it's a perfect square. It's clear. Everybody knows that. Then if we do that, we know we're going to get a squared plus 2 ab plus b squared. Then if I do exactly extract coefficients, you will see that this is 1, this is 2, this is 1. That is clear. But there's something more interesting. What is interesting is that here we've got a power 2, b power 0, plus 2a power 1, b power 1, plus a power 0, b power 2. In other words, usually we just focus on the a squared plus 2ab squared, but we don't look at another pattern. Another pattern which is there is that if we consider that these a and b we've got a and b in every term, the powers of a and b in every term, they always add to 2. 0 plus 2, 2. 1 plus 1, 2. 0 plus 2 is 2. That's one beautiful thing there. On the other hand, the other beautiful thing is, here when you're starting doing this thing, you can see now you're coming up with a kind of a triangle. And the edges there are 1, 1, 1, 1. But now this 2 is actually 1 plus 1. Do you see that? That's another thing you need to focus on. Now let's take a power 3. A plus b is power 3, not a power 3. A plus b to the power 3. If you expand this, I'm not going to waste a lot of time and expand it now. I'm going to tell you what it is. What you can do later is to check yourself that it really expands to that. This will expand to a to the power 3. And if I want to do this pattern which I had there, I would say b power 0. Then 0 plus that is 3. Then the next step, plus 3 a power 2 b power 1 plus 3 a power 1 b power 2 plus a power 0 b power 3. Now if I focus on coefficients again here, I will have here 1, 1, 3, 3, and 1, if you check that. But if you check that, what we've checked here, this 1 and this 1 make 3. This one coefficient and this one, they make that. Then the other thing which is very important, check this. Check this. This is power 2 here. The very first coefficient after the leading term is 2. It's power 3 here. The very first coefficient after the leading term is 3. That is also interesting. Now, after this, after what we've seen here, in these 3 lines here, I'm not really going to calculate I'm not going to do the expansion in a very difficult way for the power 4. If you check what's happening here, what am I going to do? I'm just going to keep my edge being 1 and then do this and 4. It agrees that the first coefficient of the thing is going to be 4. And then do this 6 and do this. 4 and do this. I'm complete. After that, everything is almost mechanical now. Instead of multiplying that thing 4 times, I just use this kind of mechanics here, and I create my coefficients and then I write. So which means when I get to a plus b power 4, I'll just go to the table there and say the first term must be a to power 4 plus the first coefficient here must be 4 power a. But the a, what happens with powers of a? 3, 2, 1, 0, which means they follow a pattern of decreasing. So after that, I just get 3, then b plus 6, 2, b 2 plus 4, a 1, b 3 plus b 4. Now, while it's not writing a everywhere, I know there is a here is power 0. Is that right? To everybody. So then I get that. When you get to far 5, exactly the same thing. Now, what is beautiful about this thing? This triangle gives us a kind of a shortcut or kind of a coding of the coefficients of binomials. Are we together? Okay. Now, these coefficients, even they can be calculated this way, they can also be calculated in another way. This term here, I can say this term is 4, choose 0. In other words, in that power 4 expression is for this one I choose 0. This one is 4, choose 1. And the next one is 4, choose 2. And the next one is 4, choose 3. And this one is 4, choose 4. Now notice one thing also which is very interesting. If the power here is 4, the terms are 4 plus 1. See here, it's 4 plus 1 terms. What do I mean by that? 1, 2, 3, 4, 5 terms. 5 is equal to 4 plus 1. If the power here is 1, the terms are 2, which is 1 plus 1. If the power here is 0, the terms are 0 plus 1. That is very, very important also. Are we together? Hello? No, you don't need to understand this. You need to see it. You see? Yeah. Because sometimes we waste our understanding instead of seeing some things and just accepting them because they are reality. Yeah, is that right? Okay. So now that's the thing. The most important thing now is to try to learn, if you don't know, what is the meaning of m choose n. M choose n. It means, I can remember I might mention something you don't know again, but I expect you to know this, that m choose n, what I'm expecting to know is to know what is m factorial. But if you don't know, don't stress, don't worry, don't feel like there's something wrong with you.
But on the video it's just
Okay, so if there's someone who doesn't understand exactly what this means, I'll explain it now shortly. Then down here, you're going to have m minus n factorial, and then you're going to have n factorial. So first, let's start by factorial, if you want to understand what factorial. I'm not going to define it like formally. I will start illustrating by example, then we try to understand what is the thing. Is that right? So if we had 5, and somebody said, please, 5 factorial, this is what I would do. 1 times 2 times 3 times 4 times 5. This product is what we read as 5 factorial. So now, if I give you n, which is a natural number, and everyone would understand what is a natural number, Then I say define factorial. I think you can see that if this is going to be 1 times 2 times 3 times, we don't know what is n, times n minus 1 times n. Do you agree? Then you write that n factorial. So now if we come to say m choose 0, which means we're going to do this. If say now 4 choose 0, I wanted to say 4 choose 0, I said m choose 0. 4 choose 0, which is going to give us 4 factorial over 4 minus 0 factorial and 0 factorial. Then here, when you think of 0 factorial, you wonder how I'm going to do this. How I'm going to do this. Maybe if you think of 1 factorial, you can just say 1 times, there's nothing else below 1, it will be 1, isn't it? Then the problem becomes, what is 0 factorial? Altogether, because I cannot count from 1 up to 0, making a product. So this becomes a problem. But now there's a gentleman's agreement. I know maybe it's not politically correct to say gentleman's agreement, but it has always been called gentleman's agreement that 0 factorial is equal to 1 is equal to 1 factorial. That's maybe to avoid the word gentleman's agreement. That's what you can call a convention. A convention is an agreement. It's very clear that there's no way you can do something like this with 0 to get 0 factorial. So just for agreement, for making things move smoothly, people sit down and agree, okay, let's try to see what happens if we work with 0 factorial. Are we going to proceed with our maths? If we can proceed, then all is fine. We define 0 factorial and 1 factorial as equal to 1. Is that fine for everybody? So now from today onwards, we know what is n factorial, whether n is 0, whether n is 1, whether n is any number greater than 1. All together? Okay, so that's the thing. So what's going to happen here now? This is going to be 4 factorial, which is going to be 1 times 2 times 3 times 4. But 4 minus 0 is 4. Factorial is 4 factorial, so it's 1 times 2 times 3 times 4. Now, this 0 factorial is 1. So which means when we multiply this product by 1, it's still going to be the same. So which means this is going to be equals to, please allow me to write like an Arab here, from the right to the left. So this is going to be equals to 1. Do you agree? Okay, so that is 1. Just look at that. That 1 is the coefficient here of that leading term. So now we can write here this a to the power 4 plus. Now let's check whether this one is also going to deliver us the coefficient for that. Now, coming to the second term, we've got 4, choose 1. Just for remembrance, you can try to remember these things this way. You can say 0 for initial term, isn't it? Isn't it? The starting point term. Then you start counting 0, 1, 2, 3, 4. Okay? Then obvious, that way you're going to have 5 terms. Are we together? Okay. So then if you choose this one, now what's going to be this? This is going to be 4 factorial over 3 factorial times 1 factorial. Everybody must read this thing into this formula and see that it agrees. Does it agree? Does it agree? Okay. Now, expanding the numerator. The numerator is 3 factorial times 4 over 3 factorial. 3 factorial times 1 is 3 factorial. Isn't it? Then this 3 factorial and that 3 factorial, they don't cancel. They make a 1. They make a 1. Then gives us 4, which is the coefficient of this second term here. Then we can write here a cubed b power 1 with a plus there. Now, you can now from there onwards do it yourself and convince yourself that yes, this is a way of getting a coefficient of a binomial to the power 4. Look at where 4 is. Of a binomial to the power 4. What you need to know is just how to calculate this. Now, this thing becomes more interesting. Like for example, I can give you a binomial like this, and they say to the power 100, and they ask you only to give me the 50th term or the coefficient of the 50th term. I can either ask for the coefficient of the 50th term or ask only for the 50th term. If you check what's happening here, check what's happening here. This is the term number 1. So this term number, second term, yes. The second term. This is the second term, is it? Okay. Now, if you check what's happening here, this is the second term. This is to the power 1. And this one is equals to 4 minus 1. Now, if I look at those things that way, then I can know the 50th term. Because what's going to happen here? The m is going to be my 100. What is going to be my number here? It's going to be 51.
It's the 50th term.
Yeah. It must be a number. Look, this is the second term. B is of the power 2 minus 1.
So it's going to be 50 minus 1,
49. So I'm going to have here a 49 here. Then I'm going to have an A and a B power 49. And then here I'll have 100 minus 49. What's going to be? 51. That will be the 50th term. So if I'm being asked for a coefficient, I will only work with this. If I'm going to the term, I'm going to work with both. So now what I've got to do now, I'm going to do 100 factorial divided by 100 minus 49, which is 50 with 1 factorial, multiplied by 49 factorial, isn't it? 49 factorial. And they have my A power 51, my B power 49. Then this is 51, eh? This is 51. Here, this one, up to 51, I'll get a 1. Then I'm left with 50, 52, 53, going that side in the simplification. But now, there will be also a 49 here. I will incorporate it. Then I simplify, I get my term. Maybe this one is exaggerated because the numbers are too big. But sometimes they give you numbers. Normally, these numbers will work out very, very easily if you've got enough patience to track the detail and the work that is done. All together. Okay, but that's one of the things about mathematics. You need to have patience and the ability to take the detail, comma to comma, dot to dot. Otherwise, once you miss one comma or you miss one detail, then everything falls apart. Are we together? So this triangle here is what normal people call Pascal's triangle. This is Pascal's triangle. So as you can see, it agrees with this and choose something. It agrees with your expansion there. If you do it manually, your expansion normal will do that thing, and that's the binomial theorem. But now, this case becomes more interesting when this power here is a rational number, or it's a negative number. Like we gave half, or we've got -2. Altogether. Now notice, if the power here is natural number, if the powers here n is a natural number, we definitely get n plus 1 terms. We have seen that. Altogether. Okay. But once the power starts being, let's say, a negative number, like n is an integer, and in this case, let's say n is less than 0. I'm talking about integers. In this case here, this expansion will have infinite terms. And when you've got infinite terms and they're being added, you no longer talk of a sum, you talk of a series. Then you get what we call a binomial series or a binomial expansion of infinite terms. Then when something which is being added has got infinite terms, then we start worrying about what is the sum of that kind of thing, infinite terms. So infinite terms will happen when n is negative, and also when n is a rational power, like half, minus half. I'm just giving examples, particular cases. For numbers like this, we still have got going to have infinite terms, which means we're going to have a kind of a series. Yeah. Then what we get there? So let's say we've got A plus B to the power n. And now n is not restricted to natural numbers. This is what's going to happen. You're going to have A to the power n. If we agree that this follows exactly the same pattern that we had before, we must agree that the first coefficient here is going to be n, and then A is going to be power n minus 1, and then B is going to be power 1, such that when we add these terms, these powers, we must get back to n. Then the worry is, what will happen as we're going to infinity? That's because this thing is not stopping. We must try to have a general term for this thing. Let's talk about this one. This one will be n choose 1. I think n choose 0 will work exactly like 4 choose 0 will be 1. Now this one, let's see whether it gives us this. Let's see. We are going to have n factorial over n minus 1 factorial and 1 factorial. But 1 factorial is 1. So which means we've got this. Now when we expand this, we are going to have here n minus 1 factorial times n. This defines the n factorial, if you can see what I'm talking about. Isn't it? Yes or no? Okay. This defines n factorial. So in the denominator, we also have n minus 1 factorial. If you simplify this, this agrees exactly. This is the coefficient there. Then the question is now, what's going to be the coefficient for the second one? Let's calculate it, because we've got a wonderful formula here which delivers coefficients of binomials. Or what am I doing there? I'm trying to say n choose what? and choose 2. So it's going to be n, choose 2, brackets. Then we do this, we're going to have n factorial over n minus 2 factorial 2 factorial. Let's be more careful here. Let's be more careful here. This will run 1, 2, dash, 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 up to n minus 2, up to n minus 1, up to n, over. This will run up to n minus 2, and go to 2, and come to 1 there, and then the product there. Guys, please make sure that you can follow what I'm doing. Don't feel irritated to ask if you don't. This is not a line. This is just dots here. Do you agree with this? Do you agree with it? What will follow here? What will follow here? Let's put this thing in brackets here. What will follow here is 2 factorial. So what's going to happen here? This and that, they're going to make us a 1. Then what's going to remain there is going to be n minus 1, brackets times n over 2 factorial, which means here the coefficient is going to be n, brackets n minus 1 over 2 factorial. The powers are going to be a to the power n minus 2, b power 2. This is 2 factorial. If we check this properly, you would agree with me that you can may as well say here, this is 1 factorial. If you also want to agree here, we can agree to say this is 0 factorial. And once I've done this, you can actually guess what's going to happen here. Look at this. This comes 2 here, and there are 2 terms of n, which means the next thing here, I'll have 3 factorial here. Look at this comes 1 here. There's only 1 term of n there. So here is 0. There's no term of n there. So if I want to come this one, I can say this must be n minus 1, n minus 2, and then a to the power n minus 3, b to the power 3, then plus dash, dash, dash. This will continue to infinity. That will continue to infinity. Interesting, huh? Interesting. But now listen to me very, very carefully. This n, I don't mind whether this n is half or is minus half. I'm going to do exactly the same thing. It's going to do exactly the same thing. For minus half, for minus n, for minus 2, minus 3, these are going to be infinite terms. Guys, I repeat, infinite terms. Okay. Then in that case, when you put a sum which is given infinite sum, we normally talk of series. But once we've got series, in adding infinite terms, then we've got a very serious problem. What is the problem? We start wondering, these infinite terms, do they add to a finite number? Is it possible to infinite terms to add to a finite number? Is it possible for infinite terms to add to a finite number? Why is it not possible? So infinite terms can never give us finite numbers. Are you sure of that? Huh? No. Let me tell you something. You guys, you are still too young. I'm going to make you grow up today. Because I'm going to show you a situation where you can have infinite terms adding or approximating a finite number.
What if they converge to a certain
That's the two things what can happen. When you've got infinite terms being added in a series, infinite terms being added in a series, there are two possibilities can happen. One is that this thing can diverge. By diverging, you keep on accumulating in such a way that it has no bound. Altogether, it has no bound. Maybe it could be going to minus infinity or going to plus infinity. It just keeps on growing, maybe in the negative direction or positive direction. Do you understand what I'm saying? Or the other thing, this can converge. And when it can converge, we can sometimes say it's less than infinity. To say it converge can also be quantified by less than infinity. So let's say I've got a summation here using this Greek sigma notation. I've got a summation to infinity of terms from 1 or from 0 of some terms like this an. So the two things what can happen, this can either do this or do that. So if I want to say this is a series which converges, I can just say it's less than infinity. Take this one, check this one. Somebody borrows you or lends you, I don't know which one is the correct, this English language sometimes, somebody lends you or borrows, I don't know, whatever. But you understand the common sense I'm doing. Somebody lends you some money. Let's say it gives you 1,000 rand. And this guy who gives you this money says, you know what, I'm very fair guy. At the month end, don't give me all the 1,000 rand, just give me half of what you owe. What are you going to pay? You're going to pay 500. Then he says the following month, give me half of what you owe. You're going to pay 250. And the next month, you're going to pay half of this. You're going to pay like 125. When are you going to finish paying this 1,000? Are they going to be finished? This is a series with infinite terms. But if you try to add these numbers, they will give you approximately 1,000. Then that's where you get now what you call altogether. Then that interest on interest, you can actually work it out. If you invest your money at the bank for a certain number of years, you will basically come up with this kind of formula whereby your capital will be there, then you get 1 plus your interest rate there times your number of years. This will give you, but that is when you're investing. Now the condition for this sum to converge, now is the condition for this sum to be less than the absolute value of R, now is R must be less than 1. Because if it's not less than 1, it doesn't converge. It will grow to astronomical numbers. At the end of the day, the bank does not have that kind of, because it's not less than 1. But actually, saying less than 1 here, you must notice that 1 is equal to 100 over 100, which is equal to 100%, which means your interest can never be high. It must be lower than altogether. So I hope you can see what's happening here. That's the thing. So now, the most important thing is you need to understand now and how to use the binomial expansion. And one area where we can use it immediately and you experience nicely is this. We have got a complex number here, and this complex number, let's say, is a cosine theta plus I sine theta. And let's say this complex number, the z, is elevated to the power 6, and then, which means now we must have cosine theta plus I sine theta to the power 6. But with our De Moivre's theorem, we know that this will reduce to cosine 6 theta plus I sine 6 theta. But binomial says this is 6 choose 0 cosine theta power 6 plus what? 6 choose 1, cosine theta power 5, I sine theta power 1, plus 6, choose 2, cosine power 4, I sine theta power 2, plus 6, choose plus 6, choose 3, cosine power 3, I sine theta power what? Power 3. Okay. Plus 6, choose 4, cosine 2, I sine theta power 4, plus 6, choose 5, cosine theta, multiply, allow me to be untied here and say sine, so I sine theta power 5. And the last term here will be 6, choose 6, and this will be I sine theta power 6. Now, this is a beautiful thing. What's going to happen here? You see that when you sort out this nicely, you can choose your I, you can do these calculations. But notice, this is very important also, notice that n choose n is equals to 1. Did you try it with 4 choose 4? The previous time, did you try it? 4 choose 4 will be 1. Yeah, so n choose n will be 1. So this coefficient is 1, and this coefficient is 1. So when we expand this, just check what's going to happen here. We're going to give cosine 6 theta. And then I, the first coefficient is going to be 6. I plus I, in brackets 6, cosine power 5 sine theta. In the next term here, what is that going to be? It's going to be 6 times 5 over 2 factorial. I'm now using the general expression. Remember? It was n minus 1 over 2 factorial. Do you agree? You don't agree? Okay, just check this. Check this. The choose story was this one. Okay, do you agree? No? Okay, so let's come back here. So now 2 factorial is 2. Then 2 divided 6 divided by 2 is 3. So I'm getting the 15. 15 what? Cosine power 4 cosine theta. And then here's sine. I'm going to get I squared, going to minus, which is going to be plus. No, I'm here. Here. That's going to be minus, because I've got to get I squared, that's going to be minus. So I've got here sine squared theta. And this is supposed to be minus sign. So we replace the sign here with a minus sign. Everybody agrees that, isn't it? Okay? Then we come to which one? To this one. Here we're going to have I squared, which is going to be minus, and then I, which is I. So we're going to get the minus I. All together.
So it's I
In brackets, we're going to do that. What are we going to have here now? We're going to have 6 times 5 times 4 over 3 factorial. But 3 factorial is 6, and that's 6, they're going to make it 1, so we've got 20. I'm following the formula. The formula said n minus 1, n minus 2 over 3 factorial. All together. Why are you getting surprised? Because when I can see, when I'm doing it, you get surprised, as if you haven't seen this formula. There is the formula.
It just has to register that you are now expecting the drop part to have 30 ends.
Yeah. When you get to this general part here, you must see how easy it is to get those factorials. Just simplify it very easily, but you must know the pattern. So in the next term, which is going to follow here, I'm going to have n minus n, n minus 1, n minus 2, n minus 3. There are 4 of them there, over 4. Yeah. So you must try, now what we must start doing, you must start to systematize that kind of a thing. Put it in your system. The only way you can do it is I'm doing it here. Also push your pen against the paper. All together? Okay, so do it. Can I see you doing it? Sit up straight, please. Yeah. So let's sit up straight and push the pen against the paper. So what's going to happen then? So that's the thing. 6, so we're going to have 20 there. Now work with cosine theta. Cosine here is 4. Here is going to be 3. Okay, so working on sine now. Sine will be power what? This is 3. So sine power of 3, and this one must add us to n, which is what? 6. So it must all be sine power 3. This is sine of theta. Plus, where are we now? Here. Are we here? Are we here? Ne?
Next door.
Now we're coming here. So this is the one. This is the one I'm talking about. Okay. Let's temporarily do it here. It's going to be 6, 5, 4, and 3 all over 4 factorial. Let's sort out I. Let's sort out I. I is going to be I squared minus 1 times minus 1. So we're going to have a plus, isn't it?
That's one.
Yeah. So let's say plus here. Then let's sort out this coefficient. This is 4 factorial is 24, isn't it? 4 factorial is 3 factorial times 4. 3 factorial is 6, and the 4 is 4 times 6 is 24. Do you agree? So, but 6 times 4 is 24. So they make 1 there. All together. Then you get what? 15. So you got 15 there. We don't have an I. What do we have there? You got cosine power 2 and the sine power 4 plus now we're here now, isn't it? Okay, let's strike something. Let's take advantage of something here. We noticed in Pascal's triangle that thing is symmetrical when we find a second. So now look, we've got 15 here. We've got 15 there. The coefficient must follow here, must be 6. The one that must follow must be a 1. We don't need to do this anymore. What are we talking? What are we doing? We're exploiting the symmetry. We're exploiting what we know. So we just need to coordinate our I and everything. The coefficients are now known. Okay. You must understand the message there. You must understand this thing in a very, very broad sense. Always when you're working, you must be open your eyes, see patterns which form, and you can exploit this kind of things, and then you shorten your working. Because if you don't shorten your working, you're going to complain and say the exercise was too long.
Yeah.
Which we know that the question is what? Is 6. So we're writing here, let's see whether it's going to be plus 6. Yes, it's going to be plus 6. Why? We're going to have I squared. It's going to be minus minus, and an I. So we're going to have an I, 6, then cosine 1, sine to the power of 5. Then plus, let's check what's going to happen with the sine. We're going to have 3I squared, which means 3 minus sine. So this is going to be minus sine. Then we're going to have minus, the quotient is 1 already. We know that quotient is 1. And then it's going to be sine to the power of 6. Then we stop there. Now, this whole expression with 7 terms is equal to this expression with 2 terms. But how do they differ? They only differ in the form of the argument of what? Of sine and cosine. So now what can we do now? This is what we can do. Okay, our results in the previous previous slide takes us to this thing. The final expansion is this one. So this final expansion of 7 terms is equal to this term of 2. But we must organize it. We must organize this. Let's organize this way. Why? How are we going to do it here? We're going to organize it in such a way that we've got the real parts. Now it's real part. I'm talking about those which don't have an imaginary label, I. So those are 1, 2, 3, and 4. Do you agree? So we write those as cos theta, that's cos power 6, minus 15 cos theta to the power 4, sine power 2 theta, plus 15 cos power 2 sine 4 theta, that's minus sine power 6, that is theta, plus I, in brackets, I collect all the imaginary parts. I will have the 6 cos 5 theta sine what? On the side, theta. Plus, which I continue this way, plus the negative 20. So let's just say minus 20. Minus 20 cos power 3 sine 3. And what next? Plus 6 cos theta sine 5 theta. Then we close the brackets. All together. So now this two-term expression is equal to this 1, 2, 3, 4, 5, 6, 7. But what does it imply? Or from what can you conclude? How can I ask the question of this one? I could have given you this and say apply the binomial theorem and whatever, and give me cos 6 theta as powers of sine and cosine. So what I can tell you now, I can now say therefore here cos 6 theta equals to that whole real part there, which is cos 6 theta minus 15 cos theta power 4 sine theta power 2 plus 15 cos theta power 2 sine theta power 4 minus sine theta power 6. That is cos. And the sine 6 theta is equals to. Then what that?
So here
But without the knowledge of the binomial theorem and the good knowledge of that de Moivre's theorem, this would be surprising. Because always in the absence of knowledge, anything is a surprise. Yeah. So when we're talking about imaginary part and the real part of a complex number, we're talking about a real number. We're only talking about the real numbers. Like for example, if I write that z is equals to 3 plus I 4 or 4i, the real numbers I can see here is 3, 4. And I see also an imaginary unit. So, but the imaginary unit there with 4 just tells me that this real number 4 is along the imaginary axis. So now when I'm saying I want the real part of z, I'm asking for 3. And then when we say imaginary part of z, we're only talking about the real number 4 without an. Please, there's that thing causes a lot of confusion always, but you must say that. So now when we are talking about sine here, sine 6 theta is not with I.
it's only there.
Yeah, that is sine theta. If they asked you to express sine 6 theta in powers of cos and sine, this is what we're going to pick without I. Is that clear? Okay. I hope this helps. And I wish to thank you for being good listeners.